Okay, for this coding challenge, the interviewer asks us to construct a BST class. BST is just acronym for binary search tree, and this class has to have three methods: its contain, its insert, and delete. So, if we start with contains, all we need to do is just traverse the tree and return a boolean. So whether we find, let's say that we're searching for 30, and if we find 30, we return true, right? And if we don't, just return false. So the traversal starts at the root node, and we just compare the values, right? If the current value is bigger than the current node's value, we go to the right. So we basically are doing, we can remove all the left subtree. Right? We're here now. We do the same. If is this value bigger than the current node's value? It is. We can remove all the left subtree, and we're finally at the node that has the same value, or the value that we're looking for, and that's why we can just return true in this case. Cool. And if we talk about time space complexity for this method, so for searching, in the worst case is O of n is the number of nodes in the tree, and that's because we can have trees that only have nodes like this. It's not balanced, right? That's why it's O of n. But if it's well balanced, right, the runtime can be log of n, right? So that's about runtime. So let's talk about the insert function. So with insert, we need to still, let's say that we want to insert number 15 in the tree. We still do the same, the comparison, and starting from the root node. So the 15 is bigger than 10. We go to the right. And now we're at 20. 20 is bigger than 15, so we need to go to the left. And we see that node 20 points to none. And we just found our place to put 15 here, right? So like this. The runtime for insertion is the same as contains. The worst of n would be of n, of course, linear. And if the tree is balanced, is logarithmic, right? Cool. And for deletion, so deletion will be a little trickier than implementing insert or contains, because we have a few, I don't know, 2 or 3 edge cases. So if we want to delete 15, what we do is, of course, traverse, and once we find the node with the same value that we're looking for, we delete it, right? In this case, 15 is leaf node, so this is the easiest case. We just go to the parent, and parent dot left points to none, right? Just change this to point to none, which is basically deletion. Cool. The next example would be to delete a node that has only one child. So let's delete 20. When we find this and find out that the node has only one child, what we do is just go to the parent. The parent to the right points to its child, right? Like this. And this would basically be deletion of node 20. Cool. The final example would be deletion of node that has both children. So 10 and 20 have both children. So let's try to delete 10, which is accidentally root node. So here there's a trick of doing this. So we cannot just delete 10 and replace it with 5 or 20. This just wouldn't work. So what we need to do is go to the right and find the smallest value from the right subtree. So in this case, it's this guy here, it's 15. So once we found 15, we can remove 15 tree, right? And because it's leaf node, it's easy. We already done that. And replace the node's value with the smallest one, which is 15 here. And that's how we basically deleted the node 10, right? Okay, so let's see how this would look in code. Let's first construct the BST class. So class BST, which inherits from object. And what we need to implement is, of course, constructor class. Let's do that. Like this. We'll be constructing 3 functions. So the first one, insert. You can just pass. The second one will be contains. And the last one is delete. Right. And we of course have to have node class, because we'll be along the way we'll be constructing a bunch of nodes, right? So this constructor class from nodes has value, has left, which points to none. This is the default value, and the right side also points to none. Left and right, like this. Cool. So we're done with node. Cool. So let's create a BST and do a bunch of inserts. So what we'll be doing this is construction of this tree. So we first insert 10, another one is 5, then we do 20, 15, and finally 30. So cool. To test this, if this construction works, we can create traverse function which accepts node, and this will be pre-ordered traversal. So this means that we're going to be printing the value and then doing the traversals, right? And because it's a recursive function, we need to first take care of base case. So if not node, we can just return. If not, we do the printing, so node value, and then traverse to the left, the right. Cool. Traverse bst.root. Right? But we need to, of course, implement the insert in order to look at this, if this works, right? Cool. So the insert. So for insertion, we need to first test if we have a root, right? If we don't have root, we just do self.root and create a node with the value and return of course, like this. If not, we can point root to the current variable, right? And while true, we need to do finding, right? We need to find the right place to insert our value, right? So if value is less than current value, we can, you need to check, of course, if not current left, we just we found our correct spot, so we can say current.left equals node.value, and we can return because we inserted and we're done, right? If not, we just need to move pointer. We need to traverse to the left, right? Like this. Cool. else if not current dot right, we are basically like here, right? We just create a new node to the right side and return, right? If not, just move the pointer like this. Cool. And yeah, let's see if this looks okay. So we're handling, if we don't have root node, we're traversing, this looks good. So now we can run our traverse function, and what we expect here is if we run this, we should be seeing the printing value of 10, 5, 20, 15, and 30 here. So let's run this. 10, 10, 5, 20, 15, and 30. That's correct. Cool. So we're done with the insert function. The next one is contains. So current can be self.root, while current, so if we have current now, we can just check if current.value is the same as value. If it is, we can just return immediately the true value, right? We find a node and it current BST contains this value. If not, elif, so if value is less than current.value, we need to go to the left, right? Oops. Else need to go to the right, like this. Cool. And if we run out of nodes, we know that we don't have this value in the binary search tree, so we can just return false like this. Cool. So let's test this function if it actually works. So PST contains 10, so 30 and 50. So what we should be getting here is true, true, and then false, right? We have 10, we have 30, and we don't have 50 in our binary search tree. So let's run this, and we don't see anything because we're not printing. This, let's run it. True, true, false. Okay, cool. So we have okay, we're finished with our contains function, and the last one is delete. Cool. So we will have few variables. So parent, let's start with none, and the current, which is just root, like this. So while current, you could also say while true, but this will prevent us from, let's say that we're deleting node that doesn't exist. We don't do nothing, right? Okay, so if current.value equals to the value we're deleting, we need to take care of a few edge cases. So if it's leave node, only child, and both children, like this. Cool. So let's have variable is leave, right? This means that the current node doesn't have left, no, current node right, like this. If is leave, right? And because we have descriptive variable name, we can just delete comment, right? It's not necessary anymore. And if it's leave node, we need to check if we have parent, right? If not parent, we know that we're deleting root node. And if it's leave, right, we just do self.root equals none, like this. If we have parent, we need to check parent.left is equal to current. If it is, right, we can say parent dot left equals to none, like this, right? Right, like this. Cool. So we just handled the leave case, and we can continue with only child. So if not left, current dot left. And of course, because it's lift node, we need to return, right? And stop. It's cool. Sorry. If not current dot left, what do we do? Well, basically, we need to check if not parent. We know that root can point to current dot right, like this, I think. Okay. Else we know that we have parent, so we can say if parent dot left equals to current, left points to what? It points to current dot right, because we don't have current dot left, right? Yeah, like this. Else current dot left, like this. Does it look good? If not current dot left, check if we have parent, else we have parent, and we're just checking where to put it. So if parent dot left, current, like this. So this should be parent dot, no, this is not correct, right? Parent dot right needs to be right, like this, right? Because we're pointing to the right because we don't have left child. And this looks correct, right? And we return because we're done, like this. Yes. And we need to handle the case when we only have the right child. So let's do that. So if not right, we need to point to the left child, like this. So left, and this gets left. Let's see. This works. Yeah, it looks good. Okay, cool. So we're done with the only child. Next one, both children. So we of course need to find the smallest, which is basically current dot right, and while true, you can say if smallest dot left, right? If we have smallest and smallest dot left, we can just reverse, like this. Else just break. And this point here, at this line, we should get smallest value, and we can do deletion first. So let's do self.delete smallest value, which is just a leaf node, and we need to do what? We need to replace current dot value with smallest dot value, like this. Yeah, I think this looks good, right? Cool. We return. Okay. The next thing we do, right, at this point, if we look, if current dot value, if it's not current value, we need to still traverse, right? So we do parent yeah, but cur and I need to go back here, like, but in the case that, okay, both children, but if we're deleting root node, does this still work? Yeah, but yeah, it still works because it's only child. Okay, cool. No matter. Cool. So the next case is if current value is not the same as value that we're deleting, we just point parent to the current, and we need to traverse current. So if value is less than current dot value, we need to traverse to the left. So current is equal to current dot left, else to the right. Yes, like this. Cool. And the final thing we need to do is just prove that this delete method is working. So let's do that. Cool. Like, if we look at the tree that we constructed here, let's first test if deletion of leaf node, which is 15 is leaf node, works. So if we delete 15, we shouldn't see the 15. Okay, we don't. Cool. The next thing, if we delete 15, then 20 has only child. We can do that. Let's do it. So if we delete 20, we should still see 30 in our output, right? Let's run it. And we do. So it's 10, 5, and 30. So 10, 5, and 30, which is correct. And the final thing we want to test is if we delete a node with both children. In this case, we want to delete 10. So if we delete 10, what we want to see is first we want to see 15 as a root node, right? Yep. Cool. So let's run it. 15, 5. Okay, cool. It looks correct. Okay, so let's recap this. It's kind of a long video, but for insertion, it's pretty straightforward, right? We're just finding the place to put it in, right? The value, and just construct a node. The same for contains, right? Just traverse into the tree. If the value is bigger, just go to the right. If it's small, go to the left. For deletion, right? For deletion is a little more involved because we need to take care of leaf node, only child, and both children, right? And that's it. Yeah. Thanks for watching, and till next time. Bye.